This is an illustration for boundary value problems. Just for a review, a two-point boundary value problem is a second order or a higher order differential equation where the value of dependent variable y is provided at two distinct points of x, which generally marks the physical boundaries of the domain. And when we get a solution, so we have a particular type of distinct solution of y as a function of x. Mathematically, we can have the boundary value problems of linear type or the non-linear type, and we have the corresponding methods to that based upon our knowledge of the initial value problems. The mathematical form of a two-point boundary value problem is the equation as d2y dx squared equal to f of x by y prime, and the boundary conditions are written as y of a equal to alpha and y of b equal to beta. So again, the general form is there, and a linear problem which is easier to solve because of simple mathematical functions. It can be written in terms of the functions p of x as a coefficient function to y prime, q of x a coefficient function to y, and r of x a function which is like the forcing function in the context of ordinary differential equations. And the other requirements are that p of x, q of x, and r of x should be continuous functions on a and b, on AB interval, and also q of x is greater than 0 for all values of x in interval a and b. But this information is important from mathematical point of view if you are interested to carry out the analysis from mathematical point of view in a much rigorous way. Let's see how do we solve the linear boundary value problems. So a linear boundary value problem is written in front of you, and also y of a equal to alpha, y of b equal to b. So we consider two initial value problems. First problem is similar to the original problem. We consider all the terms px y prime plus qx by 1 by and r of x. However, we solve this problem for a simple set of initial conditions with y1 of a equal to alpha, which is same as the first boundary condition at the first point A. However, we assume an initial condition for y1 prime of a equal to 0. Okay, this is fine. So we have to solve this second order initial value problem with one of the methods that we studied, starting from Euler method or modified Euler method or the midpoint method or RK methods or Taylor's method or the predictor corrector types of methods. We solve this one problem, and also we consider another problem which is slightly modified, slightly different than the linear boundary value problem. So we omit the term r of x, which means we solve the problem without the forcing function, and we consider a different set of initial conditions like y2 of a equal to 0 and y2 prime of a equal to 1. So we solve two boundary value problem, two initial value problems with a distinct set of initial conditions, and then in the next step we combine the two solutions. So from in pictorial way, for our boundary value problem, which is given with the two distinct boundary conditions, we solve first initial value problem and get its solution as y1 of x which is the solution of a similar in second order initial value problem, and we solve another initial value problem, and its solution would be y2 of x. And then the next step is to merge these solutions to give us the final solution, or basically an approximation to the solution of original boundary value problem. And here is the recipe. Final solution is a linear combination of two solutions, y1 of x and y2 of x. So in order to eliminate the evaluate the constants a and b, we provide the boundary conditions, and upon simplification we get the final solution to the boundary value problem is a weighted sum of two solutions, y1 of x and y2 of x. Let's illustrate this problem with an example. The example here I am considering is a second order boundary value problem, d2y dx squared equal to y prime plus 2y plus cos of x. We have the boundary conditions. And the two initial value problems, in order to solve the original boundary value problem, are here. So first problem is exactly same. However, with the initial condition y1 of 0 equal to minus 0.3, same as the first boundary condition. So we consider the initial condition as y1 prime of 0 equal to 0, and the second initial value problem will be considered uh, as without the term cos of x. So it is y2 prime plus 2y2 equal to d2y2 dx squared, with the initial conditions y0 y of 0 equal to 0 and y2 prime of 0 equal to 1. Let's move to the Microsoft Excel sheet, where we have the calculations for this two-point boundary value problem, which is of linear type. Okay, so here we are with our demonstration on linear shooting method. So the first problem we have considered is the initial value problem with the particular initial conditions. So here is the solution to this problem, and I have solved this problem with the RK4 method. So of course, a second order initial value problem, it must contain 8 k's to be evaluated. First k should be k1 y1, which is the first k for y equation, and we have to consider the second variable as u1. So the second k will be evaluated as k1 u1. Then we will calculate k2 u2. Then we will evaluate k2 y1, and then k2 u1, then k3 y1, then k3 u1, then k4 y1, and k4 u1, and then we will calculate the value of solution y1 at the next point. As you move your cursor to a cell or to select a particular cell, you will be able to see the calculations appearing in this bar. Like over here, if I read, it is B14. So B14 cell has been constructed by the calculation which has appeared in the upper formula bars. So B14, it is equal to, for example, uh, 0.314 times J13. So for example, if I make a click over here, So it is going to highlight the particular cells. So it means in this calculation, a value from J13 has been utilized. So for the first initial value problem, we have the solutions in the cells below Y1 with the titles, right, titles for identification Y1, U1. Similarly, we will solve the second initial value problem. The second initial value of problem does not consider the term R of X, and so we have to solve the problem with any of the methods. Here the calculations are based upon RK4 methods. I have highlighted the initial conditions that we have considered for solving this problem. So you may see that y2 of 0 is equal to 0, and y2 prime, which is identified in this calculation as u2, it is equal to 1. So we have to have two solutions, y1 and y2. So this is our second solution. So after that, we have to fuse these two solutions. So we have to fuse these two solutions, I mean y1 and y2, with the equation y of x equal to y1 of x plus beta minus y1 of b. Y1 of b is the value, last value of from y1 solution, and y2 of b is the last value of the solution from here, and beta is the uh, second boundary condition that we have identified from our problem, that we identify from our solution. And then we fuse these two solutions in the column y, which is identified and highlighted in this illustration. For this problem, we also have the exact solution for comparison, and it is over here. And if you go for the error calculation, so you can find the error calculation performed in the column AE. So the final thing is to plot these solutions. So we have this form. So y1 of x has been plotted as this green line. Y2 of x, it is this indigo colored line. So you can see the problem, the solution starts from 0. And if you clearly notice, that the exact solution has been overlapped by the dotted red colored line. So between the spaces of the dotted colored line, we can see slightly blue color. So that is the power of the method, and the accuracy depends upon the method that you have chosen in order to solve those two initial value problem from which you have started. Like in my illustration, I use the RK4 method in order to solve the two initial value problems.